Hello, folks. Welcome to Rational Science. We're going to have a great day today. We're going to be dealing with what? The electron? What in the world is an electron? Well, you'll find out that quite complicated, really. But before we get there, let's start with the news. Let's start with the news. Here we have a couple paper that puts mathematical physics in the right perspective. Okay. Here's one. Says James Webb Space Telescope reveals what new origin story for the universe's first supermassive black holes. They're saying that these black holes they started already a few million years after the Big Bang, when there were no stars. And remember what a black hole is or how it gets formed. It's a gravitational collapse of a star. And here they invented a new way of creating black holes. It says pristine gas clouds, which would typically fragment and form stars, instead collapsed wholesale into massive black holes. And so you have all this debris coming out of the explosion, I guess, of the Big Bang. And instead of pushing outwards like a hand grenade would, somehow these clouds of gases and particles and whatever, they condensed, they kind of came together and formed these black holes. That's what they're saying. These objects, known as direct collapse black holes, would have contained tens of thousands to hundreds of thousands of times the mass of the sun within a few hundred million years after the Big Bang. Starting from such usually large seeds helps resolve the timing problem posed by the existence of billion solar mass black holes less than a billion years after the universe formed. So at all costs, they want to explain things and they violate their own rules. You know, it turns out that the black hole was a consequence of star collapsing. Now they're saying here you have this Big Bang, it's exploding outwards. And somehow within that explosion outwards, remember the balloon analogy, the particles, the stars, everything is just stapled to the firmament, right, to the outside of the ball that's expanding. So it's here. It's the polka dot balloon theory, right? The polka dots get farther and farther away from each other. And what these people say is somehow, in spite of the fact that the balloon is expanding and pushing all the polka dots away from each other, somehow the polka dots are coming towards each other and forming these black holes. That's what they're saying. So, you know, we have all these contradictions. They cannot make any sense of any of that. It's just math to try to explain why they believe there were black holes before there were stars. Take it or leave it. Okay, that's what these people are studying and what they come up with. These are the theories. Okay, here's another one, another interesting theory, right? And that said they confirmed again, you know, that there's dark energy out there. Remember, dark energy is most of what's out there, smaller part, about a quarter of the universe is dark matter, and then a tiny, tiny bit there, you know, what is it? 3.6 non-luminous matter, and luminous matter is only 0.4%. Everything you can see out there is such a tiny amount. Everything else is stuff we can't see or touch or whatever. Anyway, it says dark energy is thought to make up about 70% of total energy, right, of the universe. Scientists propose the concept to explain what observations that suggest the universe is expanding. They're saying the universe is expanding. How can it expand if the universe is a concept? Space is a concept. So what is it that's expanding? In other words, if they're going to talk about particles, you know, matter, you can't talk about expanding. You say, hey, they're flying away from each other. But that's not what they're saying. They're saying that there's this balloon that's expanding. It's inflating, right? In fact, they talk about inflation's theory, right? And they say weak gravitational lensing occurs when a galaxy cluster warps space-time. Tell me about it. Okay, so they're warping what? 4 number lines. And then some questions remain still, right? Despite that they've proved and verified and whatever, falsified, predicted, whatever, the pattern of galaxy clustering still doesn't line up exactly with predictions from the standard model. So despite these contradictions, they just move on. They don't care. They just bumble forward no matter what. And then here's another. This was the one I liked the most, and this one's nice. It's about dark matter. Okay, here it is. Dark matter shown. So now they're going to see it. Okay, this dark matter is now going to be visible, right? Shown in newest images from the James Webb telescope. Here it says dark matter is estimated to make up about 27% of total energy. Okay, dark, and it says, but hard to detect because what? It does not absorb, reflect, or emit light. In other words, it's translucent, transparent. It's not there. In other words, there's nothing there. Dark matter also passes through regular matter like a ghost. Billions of dark matter particles, they know it's particles, each one weighs tons, right? Pass through your body every second. So why? Because they don't interact with matter, they don't interact with your atoms, right? They go right through. There's no harm. They don't notice us and just keep going. Okay, great. So they're invisible, they're intangible, they go right through us, so they don't interact with matter at all. Okay, but then it says, researchers found overlapping of dark and regular matter, suggesting that dark matter's gravity. Now here they're talking about a concept, that they never explained. Dark matter's gravity has pulled at regular matter over the universe's lifetime. So how does this famous dark matter particle that does not interact with matter, how does it pull on regular matter? Well, they do it through gravity. Whatever gravity is. This is, it's gravity that pulls them. The gravity of dark matter. So you see how they get around not answering the question. They sidestep the question. The question is, what is gravity? How does gravity work? What is mass? How does mass pull on mass? That's what you got to explain. And they get around it. They say, we don't know what this dark matter stuff is. We know it's a bunch of particles that weigh a lot, but they go right through your body. They don't interact with matter. But somehow, by magic, witchcraft, oh no, they call it action at a distance, somehow these particles pull on matter. So they pull on you, but they go right through you. Yeah, it's just math. That's all they have. They have a bunch of math that has no relation to rationality whatsoever, and this is what they feed the public. This is the news that comes out every day. Take it or leave it. That's what we have today. That's the cutting edge of science, of physics. Okay, okay. Let's get on with the subject matter today, the main course, and that is electrons. What is an electron? And people will say, well, I know what an electron is, a little bead that goes around the nucleus, right? Think again, okay? That's not what an electron is, okay? That was the baby stuff they taught you in what, maybe kindergarten, maybe elementary school, maybe even high school. It's actually taught in college as well, okay? But that's not what an electron is. We're going to find out what an electron is. And here it is. They had to start with dualities and so on. But as I mentioned last week, I wrote an article that was stopped by the powers that be, but eventually I got it through, and it was in this book, What is the Electron? Okay, by Simulik. This was out in 2005. And people asked whether I actually finally got to publish it, and the answer is yes. I made my point, and the powers that be had to take it back, or they essentially backed my argument that, yeah, it should have been published. And there's the article. You can find it there. There's the link to the article. And so you can look it up and read it. It's available to the public, so no problem there. Light, neither particle nor transverse wave. And why am I bringing this up? Because before we can get to the electron and to understand the subject matter of today, we have to go through, right? We have to go through the wave nature of light, which is later on, extrapolated to the electron, the wave nature of the electron. We start with this fellow, turn of the century, in the 19th century, from 1800 to the 1900s. We had this fellow. His name is Thomas Young. Okay, You probably heard of him, right? And he ran into a lot of trouble. And I'll tell you why he ran into trouble, because he decided to challenge Newton. Imagine they had 200 plus years of Newton, and he was a god like Einstein is today. And everybody believed in Newton. You couldn't criticize Newton. And here was Thomas Young. He said, look, Newton was wrong. Light is not made of particles. It's made of waves. And he ran this double slit experiment, right, which he essentially got from Newton, because Newton did that hair experiment. He pulled one of his own hairs, and apparently was the first one to do the experiment, but nothing came out of that. And it was Thomas Young who decided to measure and find out what the wavelength was, what the frequency, that kind of thing, right? And he came up with this notion that light is made of waves. Now, that notion had already also come from the days of Newton. We had Thomas Hook, who came up with a wave notion of light, and later on it was mathematized by Huygens, but he had these water waves. And so again, here, Thomas Young was confirming that it was some kind of wave, okay? And he got a lot of slack for that. They really didn't like what he was saying. So, he took a lot of flack from the establishment, because they were all pro-Newtonians. Okay, so what happened? We have this Newton's hair experiment, right? And I did it without the slits. And I recommend that everybody do it without the slits. You don't need to cut little slits into some kind of material and measure and do any of that. All you have to do is put a needle there, like I did there, and you can see at the far wall, which is maybe 20, 25 feet away, you can see a little light. I circled it over there at the end, and when you come up close, that's what you see. You see the fringes. So you can produce this in your own home just by getting a laser pointer and pointing it at a needle. That's it. That's all you need to do. Okay, and you'll see the fringes. So you don't need all this stuff that they try to teach you in college, that you have to cut these little slits. In fact, this is my setup. Here it is. Okay, I hope you can see that. And all you need to do is shine a laser, a little laser pointer at the needle, and you will get your fringes on the far wall. Very simple. 10 cents, maybe $1, I don't know. With inflation, maybe $5. How does the establishment explain, this slit experiment? Well, today they cheat. They use water waves. They say, look, it's like water waves. They go through a slit and they interfere with each other. Well, we more or less understand that, because water waves, that's what they do. So are we saying that light behaves like water waves? Is that what light is? A bunch of water waves that interfere with each other after they pass the slits? And the problem with water waves is that, first, light is not made of water waves. Then the question is whether you can do that with a needle. What would you get if you put a needle? Would you get the same thing you get with two slits? Okay, that's one issue. But here you have here you can show that it cannot be done with particles. Okay, because if you can do it with a needle like I did, this is what would happen with particles. Particles would hit the sides of the needle, right, and bounce outwards. They would not interfere with each other. So you cannot explain this experiment, the slit experiment, with particles, because they hit the sides of the needles and bounce outwards, okay? And it turns out that same thing happens with waves, okay? I mean, here's waves would hit remember it's transverse waves, right? They hit the sides of the needles, bounce outwards. And now you see why they use water waves, because you can't do it with transverse waves. Transverse waves would hit the sides of the needle, and there's no reason for them to interfere with each other at all. You see what they do with the slits. They have the little windowsills of the slits, and they have particles and waves hit the edge of the sills, the windowsills, and bounce inwards. That's what they do. And that's because you have these slits, these windows slit sills, right? But if you only have the needle, the part in the center, it doesn't bounce against whether particles or waves. There's nothing to bounce against to come inwards. And that's when they hit the needle and bounce outwards. So you can't explain this experiment, the slit experiment, with either waves or particles. Okay. With the rope, it's very easy, straightforward. Okay. Our model float rope. There you can see it. You know, every atom is connected to every other atom. So they're physically connected by these elongated mediators known as, which appear like this, like a rope. Okay, that's what we're talking about there. And you can see what's happening. They send a signal to an existing medium. The medium is already there. Okay, nothing's traveling except a signal along the rope, disturbance along the rope. So what you have is one atom in the source bound to an atom on the sides of the needle, and from there, that one's bound, physically bound, right, to an atom on the screen. And so you can see what you have there is simply, you know, there's a phase difference. You know, they move like that until you have constructive interference when they match, and you have destructive interference when they don't match, when they're, you know, a link of rope away. And that's what you have there. We can explain this very easily with ropes. You cannot explain it with either waves or particles. And by waves, I mean transverse waves. With water waves, yeah, you can explain it. The question is whether you can explain it with a needle with water waves. Okay, will the waves come inwards? Will they interfere in such a way that you get, you know, the fringes? And this is another vision so that you can see it a little better, maybe sideways. Okay, that's what's happening. All the atoms are already connected. Nothing is traveling. No physical object is traveling. What's happening, the ropes are already connected before you turn the light on. Once you turn the light on, all you're doing is increasing the frequency, and suddenly it comes in the visible range. And all you have is, you know, the ropes are already connected to every point on the screen, and they just turn on. That's why it's instant, you know, instantaneous. There's nothing that has to travel from one place to another. All you're doing is just turning on, you know, the rope, in the sense that you're creating shorter links and more links, meaning high frequency, lower wavelength, the link length, right? And all you're doing is putting it within the visible range. The ropes were already there before you turned the light on, before you turned the source on. Anyways, that's how the 19th century started. With a wave. 19th century was a wave century. Everybody just dealt with a wave and forgot about the particle. And here you have the second, confirmation, you can say, or reinforcement for the wave. You have Fresnel, and he's a French guy. And there were several French guys that worked on this, but he's the guy who picked up on this notion that it was really a transverse wave, because he kind of proved that to the mathematical establishment, that maybe what's happening is this picket fence mechanism where, you know, part of the wave of light was blocked by the vertical parts of the polarizer, and a second polarizer just extinguished the light altogether. Okay, that's what's happening. So he came up with a picket fence notion, and that started convincing people that what you had here was really a transverse wave, you know, and that's where the transverse wave got rolling on. You come to this fellow, his name is Maxwell. He was not a physicist, he was a mathematician. People confuse him and say he was a physicist. He was not. He never did physics in his entire life. He came up with equations. He mathematized some of the laws, as they call them, some of the observations that they had out there, and he just put them into mathematical form. Did he have an explanation for any of these equations? Well, he did, more or less. He had a notion about them, and again, based on the transverse wave, which is no such monster as a transverse wave, but that's what he came up with. And this is essentially his conclusions on what a wave really is, or what his equations did for the wave nature of light. Electric field lines originate on positive charges and terminate on negative charges, whatever positive and negative are. They never figure that out. Magnetic field lines are continuous, having no beginning or end. A changing magnetic field induces an electromagnetic force and hence an electric field, and magnetic fields are generated by moving charges or by changing electric fields. Well, that was all descriptions. They didn't know what a field was. They didn't know what was happening there. But one thing that came out of Maxwell's equations, really the most important one that nobody touches today, nobody analyzes today, is that little c equals frequency times wavelength at the bottom right. And what that tells you is two things. First, little c is 300,000 kilometers per second. That's very fast. And the question is, why is light so fast? That's one question. The other question is, why is it a constant? Okay, and why, if we increase the frequency, the wavelength must absolutely go down, and vice versa. If the wavelength goes up, the frequency goes down. How can you explain this with the wave? I mean, why can't you increase both the frequency and the wavelength and go faster than light, or decrease the frequency and the wavelength and go slower than light? Why is it a constant? Okay, that's the issue. That's the question. And a lot of people have opted to say, well, really, light is not a constant, doesn't travel at a constant speed. That's what a lot of people out there come up with because they can't answer that question. Why is it a constant? So they say, well, we can't answer that, so it's not a constant. That's the answer. Okay. With the rope model, again, we have no problem there. You see it. You can see it has, first of all, the same kind of architecture as the transverse wave. But the important thing about the rope is what you see at the bottom. C equals frequency times wavelength is the equation of a rope. Okay, that is. Why is it an equation of a rope? First, because the fastest thing you can imaginable, and why it's the speed limit of the universe, is that a torsion is the fastest thing that you can imagine. It's already connected. The rope is already connected at the other end. All you're doing is turning it on by bringing it within the visible range by increasing the frequency and lowering the wavelength. That's one issue. The other one is you can see why it's a constant, because if you increase one, the other one has to absolutely go down. If you increase the number of links, every link for a given length of rope, right? Every link has to be shorter, okay, and vice versa. So we're done. Now you see why light is a constant, why it travels so fast, and why it's a physical object, whereas the famous electromagnetic wave that Maxwell and others analyzed is not a physical object. It's a mathematical concept. Okay, and you can see there it's made out of vectors and fields, and those are just numbers. Okay, so that's the problem with a wave. There is no such thing as a wave, aside from the fact that wave is a verb. It's like saying the run moves. What do you mean the run moves? The jump jumps, or the jump moves. What do you mean the jump moves, the run moves, the swim moves? You're using a verb. You say the wave waves. What do you mean the wave wave? Wave is already moving. It's a verb. And that's the problem with a wave. That it's just fatal for the wave. There is no physical object called a wave. You have to identify the object that is waving. When you see water waves in the ocean, it's water that's waving. And when you see the flag waving, it's the flag that's waving. So you got to identify flag and water in the case of light. You got to find out what is the mediator of light. What is it that's waving? You can't say the wave. There's no such monster as the wave. Okay, so here's what the AI tells us. Says the mediator or carrier particle of light, which is electromagnetic radiation, is the photon. Okay, what is a photon? I guess a little ball, right? As a gauge boson, right? We call them bosons here. The photon acts as the what? Force carrier. What is a force carrier? You carry a force, like, you can say a force is a pull or a push, but to carry a push, to carry a pull, what does that mean? How do you carry a pull? For electromagnetic interactions, enabling what? The transmission of light and electromagnetic force across space. They're transmitting force. What do you mean you transmit force? You carry a force, you transmit a force? How do you transmit pull? How do you transmit push? You just say you push. You don't say you transmit a push. It makes no sense. You're not transmitting any concept there. And then it says the particle nature. Photons are what? Massless. They have to make them massless because they have to show why they're so fast. You can't do that with matter, because if matter travels at the speed of light, Einstein proved mathematically that it converts into energy. whatever that is. Anyways, photons are massless, quantum particles that travel at the speed of light. Force carriers, what is that? Electromagnetic interactions, including visible light, radio waves, etc., right, occur when charged particles exchange photons. Charged particles exchange photons. Okay, so, that's what they're doing. That's what they call a force carrier, because they exchange photons, little balls, I guess, because we still don't know what a photon is, right? Field mediation. Light is what? A propagation of the electromagnetic field. Propagation of field? Field is a bunch of numbers. How can numbers propagate? They're values. That's what the word field means. It's a value at each point in space. So you can't talk about the propagation of field, because field is a bunch of numbers. Numbers do not propagate. And again, it shows you that they don't do physics, they do math, and they call it physics. And the photon is the quantum of that field. Quantum meaning a little particle, little packet of energy, as they call it, a bundle of energy. Energy is a number, so they have a bundle of numbers there, and that's what they vibrate, they send, they transfer, whatever. Okay. Well, that's the notion of the wave. Then we started getting to particles a little over mid-century, about 3/4 down the century, 19th century, right? They started going into particles for the first time. They started looking at this as discrete little beads. In fact, they never got away from it, because the ether, that's what they thought it was, a bunch of background particles. Some of them say they stood still. The other ones say they vibrated. Some of them says it's the same thing as space. Others said, no, it fills space. Others said it's infinite. Others say it's finite. They had all these versions of the ether, but that's what the ether was, or light was, the shaking of these particles of ether. And here you have this fellow. His name is John Perron. He's not given enough credit. I mean, this is really the guy who came up with most of the ideas in the end of the 19th century and beginning of the 20th century. He wasn't given any credit because he was French. That's why. All the names you hear are Newton, and you hear all the British guys, but you don't hear of any of the French guys. Well, this guy's, I think it was 1876, he came up with this notion that if you take a Crookes tube, or, cathode ray tube, and you shine it and create this cross, for example, they just put that cross in there, right? Inside there's to get an image. Well, with a magnet, as you can see in the center one, you can manipulate it, and you can see what's happening to the cross by moving the magnet around. It goes up, the cross goes up, or the cross goes down. So with that, Perron was able to show that these cathode rays, whatever rays are, I think like sugar ray, maybe boxer. I don't know what a sugar ray is, but they said these rays, he imagined them as a bunch of particles, and he said, oh, we bent the ray. Yeah, you can't talk like that in science, in physics, okay? Because if they're made out of particles, you're talking about deflecting particles. You don't bend the particle, you bend the ray, because they treat the whole ray as a piece that's made of, like a entity that's made out of a single piece, instead of made out of all these little particles, which is what they had in their minds. So you're talking about deflecting these particles. So he deflected these particles. He called them particles. He thought they were particles, right? And that's when they began to say, oh, okay, but these are the negative particles. Why negative? Well, because they sent them out of the cathode, negative pole, right, to the anode, the positive pole, and that's when they started fooling around with the magnets and bending the beam, the ray, meaning they deflected the particles. That's what was happening. And for that, he was treated nicely, Perron, but they eventually gave him a Nobel Prize for who knows what. But he came up with a lot of discoveries. Here are some of his discoveries, just for the sake of argument here. 1895, he proves that cathode rays are comprised of negatively charged particles. Actually, that's not what rays are, right? They're made out of ropes that are connected from cathode to anode, but he thought they were particles. Everybody thought they were particles, and they began to name these particles as electrons, right? That's came later. In 1901, he proposes the first planetary model of the atom in his book Principles, Principles of Thermodynamics. He's the first guy to propose the planetary model of the atom. Not Rutherford, not anyone who came later, but today this guy has been swept under the rug. And he says an atom has a positive center surrounded by orbiting negative beads, because remember, he's the guy who said that the rays were made out of negative beads. And then in 1919, he came up with another really good idea, which later on was given to other people again. The sun and stars produce energy through thermonuclear, right, fusion of hydrogen into helium. And that was in his book list, The Atoms, right, in 1919. So he came up with a lot of these ideas, which is the theory, a physical theory. In my opinion, they're all irrational, they're wrong, but that's beside the point. The point is that he's the guy who came up with these notions, with these theories, and he's never given any credit for it. And he reasoned that because he says the helium atom weighs about 1% less than 4 hydrogen atoms. Remember, 4 hydrogen atoms are fused or compressed, right, to form helium. And he says when you do that, the helium doesn't weigh exactly like 4 atoms. Something is lost. And he said that extra energy is what the sun produces when it crunches 4 hydrogen atoms into helium. So that's how he came up with the notion, which is the notion we have today. Okay, and I personally subscribe to that theory. I think that that's what's happening inside the sun. I don't agree with the electric universe that says the sun is some kind of hollow balloon, and we have all this ionization going on the outside. They call plasma or whatever they call it. Right? No. I agree that it makes a lot more sense to say that the reason the sun doesn't burn out, it's not a little candle, a little fire there. It's compression of atoms that you compress 4 atoms into helium, and there's something that's left over, which are the signals going on along the rope and to every atom in the universe, right? And that's what they call energy. Okay, but yeah. That's the notion that I have as well. It's just a different explanation than what Perron gave it. And here, this is what we have today, the famous planetary model. Again, it was given credit to Rutherford and Bohr, but it really came up earlier, 1901, at least 10 years before Bohr came up with his notion of the electron circling, the nucleus. And that was already in 1901, the planetary model. Not that it's right, but I'm just saying that the guy who came up with that was Perron. Okay. Anyways, is that what we have today? Well, the answer is yes and no. We have all these dualities in mathematics. And why is it yes and no? Because that's the atom that they use for ionization. That's the atom that they use, the planetary model, right? For electricity, that's what they use for quantum jump. For all this, they use the planetary model. And then when you say, well, is that what an atom looks like? Is it a little bead that's going around and jumping back and forth between energy levels or orbitals? And they say, oh, no, that's wrong. And so what is right? Well, what is right is that it's really more nebulous. It's a cloud. It's a wave function. It's all these waves that are going around. So the electron is wave when it's convenient for them to have this duality to cover every base. Okay, that's what they're doing. They're just covering every base. And here you have one of the main guys from the establishment. His name is Sean Carroll, and he's going to tell you a little bit that it's no longer this planetary model, which is what everybody uses, by the way, but he says that ain't true. That's not the real atom. The atom is really, all these waves and whatever nonsense they can come up with. So listen to him. Don't take my word for it. Here goes. Okay, if that's wrong, why do they keep using it? I mean, why don't you use what it is, right? And so the question is, what is the electron if it's not this particle, this little bead that goes around the nucleus? And the answer is, it's a wave function, whatever that is. Mathematical wave function. And here you can see our good old friend Sean Carroll. He'll tell you. He said, "Today we just taught the final. We're just taught the final result." In other words, they go to college, right, and they memorize all this stuff. They say, "Oh, we have to memorize for the test," and this is what they're taught by rote. Okay, and they just have to recite the poem afterwards. That's all they have to do. They didn't know what was going on back in the early days. Do they know today? They didn't know that what was happening in those days. Do they know anything about that today? Have we made any progress whatsoever? And here they didn't know, I'm sorry, that little electron, instead of orbiting in a circle, it's a wave function. Oh my God, what are they talking about? What do you mean it's a wave function? What sense does that make now? So, but then you have to ask the question, what is a wave function? Yeah, good question. What is it telling us? And here, just, you should grab a beer at this point, right? Because it's going to shock you. In some cases, electrons act like waves. In other cases, they act like particles. Maybe the equation says, right? Perhaps, that if you start with an electron wave all spread out, it will sort of localize itself near some point and it will look like a particle. Turns out not to be true. The equations don't care about your feelings. It's the opposite. If you start out with localized electron wave, it will spread out all over the place. Okay, whatever all that meant. He's saying you start with waves close to, I guess, to the nucleus, and it kind of spreads out. And that's called the wave function. Okay, that's what he's saying. Whatever wave function is, wave function obviously has nothing to do with physics. It has to do with math. Math is not physics. Physics is not math. Math is a language. It's not even part of science. It's like Chinese. Chinese is a language. Do you know Chinese? No. Well, that's what most people think about, math. They don't understand it, and they say, okay, I don't. Well, we'll rely on these guys who study math. They know the equation, they know calculus, linear algebra, all that nonsense, right? And so they say, we're just going to rely on them to tell us. And so it's like the priest in the 5th century, he's the only guy who knew how to read in the town. And so he read the Bible and interpreted for the ignorant masses. That's exactly what's happening today. We have the mathematicians, they're the priests of the modern world. What they're doing is they're interpreting the equations and giving you the most irrational explanation for those equations that they can find. Why? Because they're using particles and waves. That's why. Because you can't explain the math with particles and waves. The equations, nothing wrong with them. What's wrong is the interpretation, that you're going to simulate that with particles and waves like on your computer. That's where the problem comes in. Okay, if you do it with ropes, hey, it works perfectly. And here you have what a wave function really is. It's got to do with probability. Probability, what is that? Statistics, some kind of nonsense like that. Here it is. What happens when you measure a property of the electron, like its position or its velocity or whatever you want to measure? What that wave function is doing is it's telling me the probability of getting a different measurement outcome. The wave function tells you the probability of seeing the electron somewhere. In other words, they keep treating the electron as a little bead, but they're saying, the bead is really a number, it's a value, and they're saying, look, if we measure here, we measure that, we find the electron, right? And it's in this region where we can find the electron. That's what they're saying. This is the region in which you can find an electron bead. This was just bizarre and crazy for all sorts of reasons. People didn't like the idea that probabilities were involved at all. And, that's why Einstein said, God does not play dice. He said, what? It's a question of probability. How many times, it comes up heads, tails, or you throw a dice, will it come out with a 12, with a double one, snake eyes? What are we talking about here? There's no predictability. That's what they were worried about. They said, well, there is a predictability that you can find it in this region. That's as far as you can get with the predictability. But there's no actual location of the electron because, as Heisenberg proved, when you move the ball, it doesn't stand still. And when the ball stands still, it doesn't move. Either you get, momentum or you get position. Yeah, no kidding. And he needed math to understand that. When the ball, here it is, here's the ball, okay? When it stands still, it doesn't move. And when it moves, hey, guess what? It doesn't stand still. There you have Heisenberg's uncertainty principle of indeterminacy. Okay, so here we have the notion of the probability cloud. Okay, it says electron cloud model. Instead of definite planetary orbits, electrons are described. Remember, they never explain, right? By wave function, and where the square of the function represents the probability, always this probability, of finding an electron in a specific region. So they're not telling you what an electron is, okay? They go back and forth. They say, well, the electron is a wave function. It's a wave. It's a cloud. And then they say, well, it ain't. It's where you can find the electron bead in that cloud, in that wave function, in that wave. So we still don't know what an electron is because they have to cover all the bases. They have to tell you it's both. It's this duality that they love in mathematics because it allows them to skip or skirt the question. The question is, what is the electron? They're saying, well, it's a little particle that you can find inside this wave function, which is the region where you can find the electron. Bead, particle, the little dot, the little speck of dust. And so here's the conclusion from good old Sean Carroll. He says, quantum mechanics says that electrons are not particles or waves. There's aspects of light, which is supposed to be a wave, which are particle light. There are aspects of particles, like electrons, that are wave light. So we still don't know the difference between a particle and a wave. And there you have I give you a little scenario there on the right, that says you can tell the difference whether a particle is the same thing as a wave and a wave is the same thing as a particle. Okay? There are aspects of particles that are wave-like, and they said they act like waves until you look at them. So don't look at them. And then they look like particles. There is no clean division between particles and forces. Well, maybe in the religion of math, there's no clean division. In science, in physics, particles are objects and forces are concepts. We never mix concepts with objects. They're comparing, more than apples and oranges here. They're comparing apples and love. What sense does it make? Yeah, particles are objects and forces are concepts. So you do not mix them up. You do not confuse one with the other. So there is a clean division between them. That is a very, very difficult thing to swallow. Absolutely. And physicists, mathematicians, right, are still trying to figure out what to make of it. Yeah, and they never will because they're mathematicians. They're the wrong people to be doing physics. They don't know anything about physics. They're just doing math. They're doing equations. They love to do all that calculus, all those fancy signs that they always put on the board behind them when they take their picture. They say, look how intelligent I am. I know how to read all that stuff that you can't read. Well, yeah, you put hieroglyphic, you put Chinese, I won't understand it either. I mean, so what? What does that tell you? What does that tell you about the universe? Can you tell me what exists by looking at those equations? Can you tell me, how it moves, how you do gravity, how you do electricity, magnetism? Tell me with those equations that you see up there, tell me how, this magnet attracts the other one. That's what you got to tell me, okay? And if you cannot tell me how this happens, what causes this to happen, right? Then you have a problem because all you're telling me is, I can tell you how fast it comes. I'll tell you, how many Gauss and whatever are in there. Who cares? Those are measurements. I want to know what is in there, what physical entity is bringing these two things together. And that's what they can never tell you. A mathematician is the wrong person to do that kind of work. And that's where the problem is. We have all these people and they're doing work that you're paying for, which is not producing any information about how the universe works. And they've distorted it so much that it's unreal today. Anyways, I like the way he ends his presentation because he says, Sean Carroll, because he says, quantum is irrational. Nobody understands it. Here, listen to him. Here goes.
Quantum mechanics is weird because we still don't understand it. What is really going on in this, our best, most important framework for doing fundamental physics?
Scary, is it? I mean, it's, what is it, 100 years now of quantum mechanics? A little more, because if you start with Max Planck, 1900, that's when he came up with a bundle of, the quantum, the bundle of energy. But 100 years, right? And they still do not understand it. And who was it? Niels Bohr says, don't try to understand it. Just shut up and calculate. All they're doing is math on stuff that they don't understand. And they never will, because they've got the wrong assumptions about what exists in that invisible world of Mother Nature. Is there anybody working on wave functions these days? Well, yeah, here you have some papers that came out in the last year. This is 2025, right? But you can see that a lot of people are working on this nonsense. The wave function of the universe and inflation. We develop a quantum cosmological framework in which the inflationary potential emerges from the structure of the wave function. Spontaneous wave function collapse from non-local gravitational self-energy. We show that. What do they show? That wave function collapses arises from a fundamental tension between the equivalence principle and the quantum superposition principle. And, wave function realism in the mathematization of nature, okay? And on the complex zeros of the wave function, I like that one. We studied the zeros. We studied the zeros of wave functions. Oh, great. They're studying the zeros of wave function. The wave function of a quantum S1 times S2 universe. Okay, so now we have this wave function. It's not only in the tiny world of quantum, it's also spread out through the cosmos, right? We study quantum gravity, corrections to the no boundary wave function. Great. How gravity can explain the collapse of the wave function. So now we have gravity collapsing the wave function. Okay, that's why the wave function collapses, right? When you look at it, because gravity intervenes. And it says, I present a simple argument why a fundamental theory that unifies matter and gravity gives rise to what seems to be a collapse of the wave function. And that comes out from Sabine, good old Sabine. Oh, she's so smart. She comes up with this collapse of the wave function. And she says it's due to gravity. All these people, they're working on nonsense. And, you're paying for this, because all this is ultimately supported by taxes. Okay, so you're paying for all this nonsense, all this famous research, that these people are doing. It's scary. That's what it is. Okay, so here we have the different models of the electron. Here's the electron bead. Okay, have it jumping back and forth between energy levels, or orbitals, right? And releasing energy and absorbing energy. Okay, whatever that is, their little green arrows, that's what energy is. Okay, that's one version. That version is the one they use for ionization, electricity, and, quantum jump. That's the one they're going to use there. That's the one they're going to show you. And you say, okay, I understand that, because it's a little bead that goes back and forth. What we don't understand about that is, why doesn't the electron bead fall all the way to the nucleus if it's negative and the nucleus is positive? Or why doesn't it spontaneously just fly away? I mean, what keeps it going back and forth between energy levels or orbitals or whatever? Okay, and the answer to that is it's a bunch of waves. So here you have the wave nature. And again, you can see that they usually have a little particle at the beginning. So it's kind of like contrails of the particle. That's what they call a wave. That's how they illustrate it, at least, right? Here you have the cloud model, okay? It covers the entire nucleus, right, all around. Okay, so you have these clouds of whatever energy, whatever that is, right? It's the region where you can find the particle. Again, this is just mathematized atom, or electron. It's got nothing to do with reality. It's just, look, that's where we can find the electron bead, somewhere around that cloud, okay? And then you have, the wave function version, which is, from the center outwards, like good old Sean told us. It's not that it comes from outwards inwards. When you look at it, it's the other way around. It comes from the inwards outwards, okay? So it just kind of expands. And again, they're talking about a region of values. They're not talking about a physical object. They're not telling you what the electron is. They say, this is where you can find the electron, what? Bead. So we still have the bead. We still have the planetary model They just kind of, you know, shield it from your understanding by saying, well, it's the region where you can find the electron bead. But they don't say it in those terms. They just say it's the wave function. You say, oh, that's that's over my head, you know. That's the wave function. Okay, so here we have a fellow who tells you that, again, reinforces that the electrons somehow are waves and particles. They're not really particles, they're waves, clouds, wave functions. Listen to him. He's a physicist. He should know. Here it goes.
Since the size of a hydrogen atom is approximately 10 to the power of minus 10 meters, and it has only one electron, that one electron can spread through the entire atom. It is truly amazing and confusing how a single electron can spread out through the entire atom. This is the wave nature of matter. In particle form, we can pinpoint the location of an object, but when it's in wave form, how can we measure its location? The wave nature of particles is not only formulated through mathematical calculations, but also proven by experiments.
Okay, so they proved it. It's a done deal. You can't challenge that anymore because they proved it. I mean, if you prove something, what are you going to challenge? Especially the entire mathematical establishment. They proved that, yeah, that it's this little fuzzy ball, right? But so what they did was they replaced the bead, right, with this cloud model, wave function model. Looks more or less like this. Okay, the one on the left clearly is the bead, and they're replacing that with this fuzzy whatever nonsense, waves, wave functions, whatever that is, right? So what are we looking at? What are those squiggly lines that are going around the center of the hydrogen atom? What are those lines? What are those waves? What are those wave functions? Well, they're a bunch of numbers. That's what it is. And so now we're going to go in there. We're going to replace the that wave function, waves, whatever, that fuzzy lines, whatever those are, right? And we're going to replace it with a ball of yarn. That's what it is. That's what they've been studying all these years. We have an actual physical object. We're saying it's a ball of yarn, right? And here they are in motion. Okay, you can see what they're presenting, what we're saying. This is what our atom looks like. Okay, and what our electron, the electron is that shell, that membrane, right, that encapsulates the proton star. And it's not like Rutherford says that it's mostly empty space. It was between his ears, he has empty space because he said, I found out that stuff goes right through there. Yeah, he didn't realize that there are objects that you cannot touch. That's where Rutherford failed. And there is an object there. There are all those single lines. You can see the double line coming into the atom, but the single line, the blue single lines go all the way through the center out the other end. Those rays, those lines, those are single threads that make up the rope, okay? And here you have a construction of the atom so that you can see what I'm talking about, why that's the case, okay? We have a magnetic thread and an electric thread. The electric thread goes through, magnetic thread goes around. Those are just to keep with convention. That's why we call them like that. There's no difference between the threads. And the electron shell essentially encapsulates the proton star, which is made of all these little lines, these little threads, single threads, right? And every atom is connected to every other atom in the universe. And there you see the ropes coming in and only a single thread, the blue one's going to the center. Okay, so here it is one more time. Electric thread goes through the center, right? And in all directions, also inside the atom. And the magnetic thread, again, arbitrary words, it's just to keep with convention, creates this ball of yarn that encapsulates the proton star. And you have all the ropes from every atom in the universe converging upon our atom. Okay, that's what we're showing there. Okay, so that's our version of the atom. And here you have a quantum jump according to quantum mechanics, according to the rope model, okay? And you can see the atoms are pumping back and forth They're triggered by every atom in the universe that, the ropes are converging upon our atom, and that's what's making it vibrate like that. And by vibrating, it also affects every atom in the universe. So it's mutual. Our atom affects every atom in the universe. Every atom in the universe affects our atom. Why? Because they're all connected by electromagnetic ropes, not waves, not particles. It's ropes. They're already connected. All we're doing is turning on the frequency, either to bring them within visible range, right? And what that does is stimulate an atom begins to pump within the frequency of visible light, and that's why we can see the atoms. In other words, a bunch of them, like molecules, right? Because they're vibrating. They're vibrating at the right frequency that allows us to see. Why? Because every atom is connected to your eye also through a rope, and it's sending that signal, higher frequency that allows it to come within visible range, or lower frequency if you're going into X-ray region or gamma rays, right? So now it brings it within the visible range, and that's why you can see objects, right? Because your eye is made out of these atoms that form molecules inside your cells, right? And that's why you can see. You can see because every atom in the universe is connected to each other, physically connected. And of course, with that, you can also explain gravity, because now you have a physical connection. But you can see the difference between quantum mechanics, a little bead going around and sending, these waves, one-way waves, right? Whereas ours is a two-way mechanism, diametric signals, going back and forth along the same rope. So you can see it's a different model altogether, okay? And it's a physical model, not like the garbage that comes out of mathematics, Cambridge and Harvard. All they have are all these nonsense equations. That's all they have. And they give it the best interpretation they can within the world of particles and waves. That's all they can do. And what we've done is got rid of the particle, got rid of the wave, and replaced it with something more physical, which is a rope. People say, well, Bill, what's the difference between a pair of fields and your rope? Well, just do this on your own time, right? Go to the hardware store and ask them for a rope, and they will give you something like this. They'll say, here it is, you got a rope. Okay, now ask them for a field. See what they give you, or for a vector or whatever. See, try it. Try the experiment. Try it twice, because it's got to be scientific, it's got to be repeatable. Okay, so this is the universe according to bgaede. All the atoms in the universe are physically connected. Okay, they're physically connected. Okay, and that's why we can not only answer, gravity. Here you have my important billion-dollar experiment, the falling of a spoon. And why does a spoon fall downwards? Well, not a single mathematician can tell you why. What causes this to fall? And the reason they can't is they never figured out that there's something physical here, that we can pass right through it. We can't touch it. We can't see it. But there's something physical here. Every atom of this spoon is connected to every atom on Earth, but we cannot see or touch the mediators. That was the secret. The secret is we can't see or touch the mediators. We can't see or touch the mediators of magnetism. There's something here. You can see, you can feel it pull on you already. Nothing's pushing my hands. The pull is on the inside. And the question is there something here? Well, there had better be. Otherwise, you're doing witchcraft. You're doing what mathematicians call action at a distance. No, there is something there that we cannot see or touch. The secret was see, touch is not the definition of an object. An object is that which has shape. All objects have shape. Not all objects can be seen or touched. You can't touch the table that the Klingon has on the other side of the universe. You cannot touch the table, the chair that I'm thinking of. You can't touch that one. So is the word chair does it not designate a physical object, the word chair? Hopefully the chair is always a physical object, right? The one I'm thinking of, the one that's on the other side of the universe, and we can't touch those, let alone see them. Okay, with that, I will see you next week, and hopefully you keep all your electrons with you, wave functions, whatever you have there, your waves and wave functions.